So our next speaker is Vedant, and he's going to be talking about this sort of model.
Thank you. Hi, good afternoon. My name is Vedant Puri, and I study at Carnegie Mellon University in mechanical engineering. And today I'll be talking about model order reduction with smooth neural fields. This is a project that we've been working on for the past year, and we're really excited to share our results with you. Okay, cool. So what you're seeing on the right is the solution to a 2D burgers problem. Now, although the Reynolds number is moderate, this problem was very intensive. We employed a Fourier spectral PDE solver, and it took over 500,000 degrees of freedom to capture the solution accurately and over a wall time of like 13-14 seconds on the GPU. Now, our model reduction approach, which is smooth neural field ROMs, is able to reduce the dimensionality of this problem from 500,000 to 2. And furthermore, the speed up we have achieved is about 200 times. Also, if you look at the diagonal profile of the solution, we see that our approaches, which is the blue and the red lines, capture the solution, including the steep shock very accurately, whereas the comparison models fail to do so. Right, so the crux to our method is that we are able to ensure accurate online dynamics evaluation of the reduced state, although all of our contributions are going to be on the dimensionality reduction side of things. So the way this works is the following. We have two defining features of our method. The first one is that we learn reduced trajectories, which are very easy to traverse. So the plots over here are essentially the distribution of ROM states. So these are the reduced coordinates, and every point on these plots corresponds to one full solution snapshot. Right, so the red curve is the projection that we learned during training. So this is the POD matrix or the encoder of your autoencoder model. And this is the ideal trajectory that your ROM snapshot should follow for minimal error. Although we see that the online solve for typical autoencoder type methods actually deviates quite significantly from the learned from the projection, which leads to accumulation of error. We fixed this issue and learned trajectories which are so simple to follow that we can actually increase the time step size in the ROM to get the faster evaluation. The second feature is to do with the neural network representation. Now, neural network representations are amazing when it comes to adding or subtracting. They're seamless, they're just functions. But when it comes to differentiation, what we have found is that they have a lot of latent high-frequency noise all over the place. And when you differentiate, the amplitude magnifies and the solution becomes essentially full of noise to a point that you can't actually capture the dynamics, the RHS of your ODE or of your PDE. So when you have to take the Laplacian or the bilaplacian of the solution, you will be in trouble because you can't actually capture the dynamics. Right, so we solve this issue by learning neural network representations, which are inherently smooth. So they actually do not have any of this high frequency noise. Okay, so one slide primer on model order reduction. I promise I won't take too much time because my predecessors have done a very good job at covering the contents. PDE is straightforward, partial U, partial T equals some right-hand side, which is critically parameterized by this parameter mu. Okay, so the full order model essentially applies a spatial discretization. So in the previous case, this is a trajectory where each point is a vector of size 500,000, and that evolves in time, right? So the model order reduction component, the first approach is linear POD ROM, which we know leaves a lot to be desired. You can see the errors between the orange curve and the red line are quite large. The second approach, which is the machine learning type method, machine learning based methods are actually able to capture these high dimensional curves with a very small number of degrees of freedom, in this case 1. But note that although these methods are very robust, they do not provide us with a very high accuracy. So the best accuracy we can expect with these machine learning methods is about 0.1%. Okay, so now that we have covered some model order reduction methods, now the second component is the time evolution, for which we are using Galerkin projection. I think William did a very good job at covering how Galerkin projection works. I'll be talking about just the collocation method, which says the following. So we take the initial solution that is provided to us by the PDE, and we project that down to the ROM manifold, and we evolve the solution on the ROM manifold, where the equation that's evolved is in fact a very low order problem. So so the util over here only has 2 or 3 degrees of freedom, right? So that's what gives us the immense speed up. Great. So what happens with typical unsupervised learning methods, such as autoencoders, which are the state-of-the-art machine learning-based ROMs, is that they learn to compress and decompress image type gridded signals between high-dimensional image space and a latent space and back. And the hope is that in learning the mappings for compression and uncompression, they're learning some meaningful representation in the latent space. And that's true for the most part. But when we apply these methods to the problem we were talking about, the 2D burgers case, we see that it starts off very well, but as the solution evolves in time, the error starts to accumulate, and by the end, the prediction is missing the solution completely. Okay, and this in fact corresponds with the latent trajectories deviating significantly. So you can see the green curve actually deviates quite a lot from the projection curve, which is in fact, the projection has an error of 10 to the -6, -7, so it's virtually indistinguishable. Okay, so we thought about what gives rise to this issue, and we tried to think about how to get around it. One approach we spent a lot of time working on is the following. This is called the auto-decode method, which is another unsupervised learning approach. Here, you're basically removing the encoder and learning the latent vectors corresponding to each snapshot in your data set directly. Right, so you're doing back propagation to learn the latent vectors instead of learning the encoder. So what we saw, quite surprisingly, was that the latent space distribution with these kind of methods is completely disjoint, and this is actually terrible for dynamics evaluation. Because if your time 0 is over here and time 1 is over there, how are you going to make it through without incurring large amounts of error in between? Right. So what actually the encoder was doing wasn't providing a sense of continuity to the latent space trajectory. So we in fact made a bad move by removing the encoder. Now the question we are looking at is what prior to place on the latent space to ensure that the traversal in the online solve is accurate and smooth. So let's look at the reduced equation. So this is a du dt equals j pseudo inverse f. We have no control over f. It is the RHS evaluated at a bunch of hyper-reduced points, collocation points, I should say. And j is going to be the Jacobian of the ROM ansatz. Right, so we don't have much control over j or f, and neither do we want that. What we want is to ensure that j pseudo inverse f is something which is near constant, really consistent, so that the trajectory doesn't undulate so much. And the way we get around this is kind of convoluted, but it's the following. Since we're doing supervised learning, we actually say, okay, instead of having the encoder that tells us what the latent trajectories are, we're just going to use time and mu, the parameters, to learn a mapping directly to the latent space vectors. And I'll show this in the context of the entire pipeline in a second. But the key idea with this is that we can control the complexity of this mapping. We can choose what neural network to be, and we can even make it a linear approximation if we want it to be. But we can make it a very small neural network and add tons of regularization. So this mapping can only be a very simple function. Right, so the entire training pipeline is as follows. We have a PDE problem, and we take parameters and time. We take the parameters and time and learn the latent space coordinates. We see that the latent space trajectory is necessarily smooth and continuous because the model Z is only able to approximate smooth and continuous functions. And then we concatenate the latent vector with the spatial coordinates and pass it to the decoder MLP. Right. So at the end, this becomes a supervised learning problem as opposed to an unsupervised learning problem. And in all our experiments, the projection error was always 10 to the minus 6, which is the best we can expect. Right. So the key idea is that if our latent space network C is going to be a really simple function, then G has to take up some of the complexity, which is completely fine. This is just a modeling assumption that we are completely free to make. Okay, so the second contribution we've made is on the neural network representation method. So as I mentioned, the assumption is that if you have a neural network that is regressing a function u, and then we take derivatives of the neural network representations, we expect the derivatives of the representation to match the derivatives of the signal. But that's absolutely not the case, and we've talked about how this high frequency noise accumulates. And the way we solve this issue is the following. We're presenting you with two approaches that are able to regularize the neural network so that we learn a smooth solution which has none of this high frequency noise. The first one is called Lipschitz regularization. Without going into a lot of detail, it penalizes the Lipschitz constant of the neural network. We're able to compute the Lipschitz constant of every layer because it's just a matrix vector product followed by a function application. And if we can compute the Lipschitz constant of every layer, we can multiply all of that up and get an upper bound for the Lipschitz constant of the entire MLP. And that's what we seek to minimize. The second regularization technique is to minimize is to directly look at what the high frequency components are present in the derivative of a neural network and to minimize them directly. So in the particular neural network choice that we were using sinusoidal neural networks. So in the derivative expression, there's a cosine term. And in the cosine, we have these W's. So when these W's are large, we have a lot of high frequency noise. So we directly penalize W with the hyperparameter that decides how much noise we want. The key here is that if we over-regularize, we will completely miss the steep shock in the solution. So we definitely have to take some time to pick the hyperparameter. But in our experiments, we found the choices to be very consistent. All right, so let me go on to the results. Okay, so this is the 1D Kuramoto-Shevashinsky equation, which is a fourth order PDE problem. And what we see is that this problem is a very diffusive case. So even POD-ROM is able to do very well. But we see that specifically our two methods, the smooth neural field with Lipschitz and weights regularization, the red and blue curves, are capturing the solution exactly, meaning that we are able to approximate the fourth order spatial derivative of the solution to an acceptable level of accuracy. And even when we look at the evolution of error as a function of time in these plots, we see that the error is incredibly low for all of these cases. The convolutional autoencoder method does pretty well for the baseline case, but when we bump up the time step size by 10x from some baseline time step, our two methods maintain the same accuracy, whereas the convolutional autoencoder blows up. Right. So this is the 2D Burgers case again, where we are looking at the traveling shock problem. We see that we are capturing the solution extremely well, as is reflected by errors which are both sub 1%, whereas the convolutional autoencoder simply blows up. Okay, so these are the solution snapshots at the last time step, and we see that the convolutional autoencoder is missing the shock over here, as is described by the magenta over here, whereas our two methods have near like 10 to the minus 3 error everywhere. We also conducted a comprehensive study of speed up as a function of the time step size we are employing and the number of hyper reduction points. In the interest of time, I'll skip that, but I'm happy to talk about this in the question answer session. And again, we have also conducted a comprehensive study of parameter interpolation and extrapolation to see how well our methods behave in comparison with the baseline convolutional autoencoder ROM. All right, thank you so much for your time. I really appreciate your attention. Please scan the QR code to look at the paper.
The resolution of the tool model you use, is it before you choose that resolution? Have you done some sort of convergence study, whether you actually need that much?
We didn't do exact convergence studies, but what we found was that any smaller resolution, and we end up with not an ex and we end up with aliasing errors of some sort, or like some sort of like noise in the solution. So the full order model we were using is a Fourier spectral PDE solver with about 512 by 512 grid points. So it's not truly a lot, but I guess it's still like 500,000 degrees of freedom on a memory limited GPU is quite a lot. So the memory expense of the full order model was about 600 gigabytes of GPU allocation, which is insane. Our GPU was about 11 gigabytes of memory. So obviously it's going to call garbage collection a bunch of times, and that might have contributed to this issue. If we go down to the slide on the results, we see that the memory footprint of our ROM with hyper reduction is in fact something of the order of 200 megabytes. So that is a significant reduction in the compute cost.
Any like viscosity or filtering in these things, or is it just pure spectral?
What's the word when you like take 2/3 of the
Anything like shock capture for it, or is it just pure discretization?
Pure discretization. I'm not sure what history variables are. Could you explain? I'm not familiar with those problems. We can talk in detail afterwards.
So I'm thinking of like using this for some more turbulent like fluid cases, and I guess like you have to increase the width or maybe the depth of the neural network to represent these highly turbulent features. So would that sort of blow up the spectral
Yeah, that's a great question. So in fact, in my contribution slide, that's exactly what I was talking about. And I guess the bottleneck with these kind of methods is that the training time is in the order of a few days for this case, whereas if I just have, let's say, 256 points, it's about 5 minutes. So it's a big range. And the fundamental issue is that these neural network representations are not very good at approximating functions to a very high accuracy. So in order to actually get that done, one plausible way to do this would be to use these new multi-resolution type architectures. People have been working on them for a long time in the computer graphics world, and these kind of methods promise training in a matter of seconds, as well as accuracy, which is fairly high. Yeah.
I have one real quick. If you had an inviscid problem
Mhm.
and have the viscosity term,
Mhm.
would you still need to use your gradient correction thing or smoothing thing that you're doing?
So the smoothing thing is only relevant for the neural network representation. It's kind of independent from the PDE we're solving. So in fact, we did solve the advection equation in 1D and 2D in the paper. So, and they did not have well, they use the same hyperparameters. Does that answer your question?
Oh, yeah. I mean, I'm saying that you're using a weak formulation of the PDE, the derivatives don't actually show up.
No, so we're using a strong formulation of the PDE and just solving at the collocation points.
Okay.
Well, if there's time, you can elaborate about
Oh yeah, of course. Well, I would say that we did something very straightforward in this case, and we only did subsampling on a uniform grid. So we had the form grid of 512 by 512, and we just subsampled down to 8 by 8, 16 by 16, and so on. This was done in the interest of time, but I think comprehensive study on hyperreduction would be beneficial for the future. Although this simple approach did work fairly well for these cases.
Okay, let's take our speaker.